Good morning and welcome to NASA's Asteroid Industry and Partner Day. We're really excited that you guys came and joined us this morning, and also for all of you that are tuning in online through our live Ustream of this particular event. Keep in mind that it's also going to be recorded and posted on YouTube, so if you'd like to share with your friends after or rewatch it, you'll be able to do so after the event. I'm Jen Gustetic. I'm the Prizes and Challenges Program Executive within the Office of the Chief Technologist, and I'll be your moderator for today's event. We have an exciting morning ahead of us. We have a lot of esteemed senior leaders from NASA here to share a little bit more with you about NASA's Asteroid Initiative. First, we're going to start with NASA's Deputy Administrator, Lori Garver, followed by the White House Office of Science and Technology Policy's Tom Khalil, who is the Deputy Director for Technology and Innovation. And followed by that, we'll have an esteemed panel of senior leaders to talk about the asteroid mission. We have Robert Lightfoot, our Associate Administrator, John Grunsfeld, our Associate Administrator for the Science Mission Directorate, Mike Gazarek, the Associate Administrator for the Space Technology Mission Directorate, and Bill Gerstenmaier, the Associate Administrator for Human Exploration and Operations Mission Directorate. And finally, we'll wrap up with Jason Kessler, who is also of the Office of Science and, of the Office of the Chief Technologist here at NASA. We will have time for question and answers throughout, so after the panel there will be time for questions, and after Jason Kessler speaks there will also be time for questions. So I'll explain a little bit more later how we're going to manage that between the in-room questions and also the social media questions. If you're tuning in from somewhere else, you know that this is being broadcast live right now on Ustream. Also, you can share your thoughts about today's event with the hashtag NASA Asteroid, as well as asking questions to NASA during the Q&A period through the Ask NASA hashtag on our Twitter account. Remember to follow NASA also at the various social channels that we have, Twitter, YouTube, Facebook, Google+. We have a number of them, as you can see on the screen. Moving on to the program, we're going to start this morning with Lori Garver. Lori Garver is NASA's Deputy Administrator. As Deputy Administrator, she is NASA's second in command. She works closely with the Administrator to provide overall leadership, planning, and policy direction for the agency. This appointment marks the second time she has worked for NASA. Her first period of service to the agency was from 1996 to 2001, when she ultimately served as the Associate Administrator for the Office of Policy and Plans. She developed her love for space while working for Senator John Glenn from 1983 to 1984, and has served in a variety of senior space-related roles in the nonprofit, government, and commercial sectors since then. Please welcome Lori Garver to the stage.
Thank you very much, Jen, and good morning. It is great to see all of you here. We're very excited about both what we're talking about today and some of the new things we're going to share with you as well. Today is all about asteroids, as you can see, and what we're going to try and do is frame the agency's existing activities and talking about how we're going to leverage those with, as we say in our title today, Industry and Partner Day. So lots of you are hopefully here to listen so that then you will have the opportunity to share your ideas on how we can carry out this important work in the most meaningful way possible. So as we do advance our activities here at NASA, we know our goal ultimately as we drive science and technology into space is to benefit those of us here on Earth who, as taxpayers, at least in the United States, help pay for this. Lots of you have seen these slides. We've been using them since the budget rollout, so today I'm just going to frame them briefly in how they relate to asteroids. So if you look at new knowledge and scientific discovery, asteroids are one of those unique, really current activities that technology has allowed. We know a lot about asteroids, just a lot more than we did 20 years ago. We have been able to detect more asteroids and actually characterize them as well. So we are focusing on this because, there you go, the next benefit, it has some economic benefit. NASA's in this for the long term, and we know as we develop space, we're not going to always do it on the backs of taxpayers, and we're going to utilize space resources. And some of those space resources might even be able to help us here on Earth economically, even more the investments we're making today. And finally, that benefit of being able to protect the planet and really advance, I think, society is something that is a very well aligned benefit with our asteroid work. We know that the dinosaurs existed only until they had the asteroid impact. That itself is science that has really taken place and developed in our lifetime, and we want to be able to prove that we are, in fact, smarter than the dinosaurs. As we go about doing this work and providing this benefit to the public, we know we want to do it in a way that really advances innovation and provides all those benefits. So we have to take and utilize our assets, our people and our institutions in a way that really allows us to focus the government dollars on what we do best while allowing partnerships and the private sector to come in and innovate and take us further. We know that is what NASA has done throughout our more than 50-year history, and we are building on that in new ways as new technologies allow us to do that. Always, always keeping in mind that we need to do it in the most efficient way. So with asteroids, of course, we know we play a role in this. We have historically taken a lead in identification. We are now taking the lead in some mitigation activities as well, but we aren't the only players in this. We have our sister agencies in the U.S., we have our commercial industry partners, and we have international partners as well. But this is all in the context of the broader NASA activities. So we have a strategy that is a robust space exploration program. We recognize that asteroids are just a piece of that strategy. So quickly to outline where it is that NASA's investing its interest these days, starting with aeronautics, very close to Earth, providing, again, those benefits, economic as well as social, as well as science, driving out Earth sciences in low Earth orbit, heliophysics, understanding what it's like to live with a star, providing all of us with the ability to live. Going out to the space station, our foothold to the universe. Human space flight, astronauts living and working on the space station today. And getting there, hopefully, very soon, our astronauts, already our cargo, in those innovative ways that provide real economic benefit and allow NASA to only be one piece of the market, our commercial crew program. While NASA spends less on that low Earth orbit transportation, we aim to go further right here with the Space Launch System, with Orion, and ultimately to that first destination on our way to Mars is the asteroid through the asteroid retrieval mission that we'll be describing in greater detail today. Going beyond that to Mars, first robotically, as we know we are, with Mars Curiosity, with MAVEN that we'll be launching later this year, going further out on our way to Pluto, and the Webb telescope, which is on track to launch in 2018 to allow us to see even further than ever before, driving that innovation, new knowledge for the benefit of all. And what we're doing are aligning those orange highlighted programs are aligned, already existing, to advance the asteroid rendezvous mission, the asteroid retrieval mission. So why? Why are we laying out asteroids specifically? Of course, we know that they carry those very secrets to the origins of life, and we have had an interest in them throughout our history. As I mentioned, we have learned even more recently through detection capability. When you look at the rate of discovery over the last 30 years of asteroids, this is truly a science that is in its renaissance. We started, when you look at electronic imaging, before electronic imaging in the 80s, we only knew of a handful of asteroids. We then in the 80s started being able to see tens of thousands. Today, we have categorized through our dedicated programs. The count is now at over 500,000 asteroids. That's within 30 years. We knew about so much that is in our solar system before, and asteroids are one of those new things. And what this program does is invest just a small fraction of NASA's budget to focus on capitalizing on the technology that has allowed us to get this new science. So what we're going to describe today are both our mission of the asteroid retrieval mission that weaves in science, technology, as well as human spaceflight. It really does leverage on existing activities, and the panel that Jen described is going to talk more about that today. We're also going to talk about our focused Grand Challenge effort to find all asteroid threats to human populations and know what to do about them. This is something that we are thrilled to be a part of. Again, NASA's not the only player in asteroids. We know that, and Grand Challenges are about leveraging those additional partners. So we are today going to be looking not only for partners and innovators and industry to get involved in the Grand Challenge, but also in our asteroid retrieval mission. So let me try and make it as clear as possible with the terminology that we use. So overall, NASA has an asteroid strategy. As I mentioned, we have for a long time. This has been largely focused in SMD, in the Science Mission Directorate, things like OSIRIS-REx and Dawn. Those activities continue. What we are initiating is the initiative that seeks to, both within the mission and within the Grand Challenge, leverage on those investments. So focusing in on the initiative that we're going to be discussing today, we have both the mission. We're going to give you further details of the maturity of this system, how it is being refined, and the whole mission concept, and hopefully put some seeds in your heads to how you can help us accomplish that in the most innovative and efficient way. We're also going to outline the Grand Challenge effort that will hopefully initiate a dialogue with you to see how it is that we can leverage those assets. This is the additional $20 million that we have requested in the 14 budget to find asteroids and begin to characterize them. So only some of this is new today, but we have outlined the mission aspect of this previously when our budget rolled out, and I'm here to tell you we were very excited by our bipartisan support, the reaction to the mission. You've got both Senator Bill Nelson talking about how clever the initiative is, and Representative Mo Brooks saying that he believes it is a good direction to go. We know that the Keck study team, and under the great leadership of a number of people, this particular quote from Tom Jones, really saw the value of the advancement of the technology that we have and how that could be leveraged with SLS and Orion to have this initial destination in translunar space. And then ultimately, Neil deGrasse Tyson, the person who outlines, I think, beyond just NASA, but to the public, was very excited about the initiative as well. We also had a great reaction from our international partners. From ESA, Jean-Jacques Dordain's talking about not only having already been involved through their contribution to SLS Orion with the service module, but they are very excited to talk about further partnerships with us, as well as our wonderful partners, the Russians, who, of course, have, for some reason, more up-close and personal experience with asteroids than the rest of us right now, recognizing the value, and even the Japanese, who perhaps have done the most, other than the United States, with interest in asteroids. A lot of international interest in partnering with us. The public also is pretty excited about this activity. We had an overwhelming reaction from the media, continue to have that today by the looks of things here, and we are absolutely thrilled to be able to share even more details with you today to talk about what it is that I think has captured the public's imagination about going out not only to protect the planet, but also to explore and to be able to leverage what we have done on our way to Mars. Specifically in the planetary defense realm, we could not literally could not be more excited by the bipartisan support this effort has. I think the Science Committee under Lamar Smith's leadership has had 2 hearings of their first handful of hearings specifically on this topic, and as you see here, is extremely supportive of NASA's efforts at detection. We also have bipartisan support on the committee, and of course, Congressman Dana Rohrabacher, who's provided leadership in this arena for decades, recognize the value that NASA has and also the leveraged value that NASA will bring with partnerships to this activity. So ultimately, our challenge statement is this: to find all asteroid threats to human populations and know what to do about them. And we know we have had this charge for a long time. Really what we're doing today is to be able to communicate that in a way, hopefully, that will allow even more people to let us know how they can help us meet this challenge. I want to leave you with this. Citizen science, innovation outreach is not new. It is not new to science. It is not new to NASA, although this picture was before NASA was even born. In 1956, the Smithsonian Institution put together teams of citizens. Teams came together across the country, over 200 teams, to help identify the first artificial satellite. This program evolved, and citizens looking for artificial satellites throughout the country, again, before NASA was even in its formal existence. We have a rich history in this. We know we drive innovation. And we also know this initiative takes nothing from the other valuable work. The reason I wanted to go through our entire portfolio is because this is only a small piece of our overall strategy, but it is an integral piece. We know it provides that initial destination for SLS Orion, but it takes nothing from the moon. It takes nothing from the moon. We know that we need this infrastructure to go to the moon, and we know from the vantage of translunar space where we will have even more capability and science and reason to go back to the moon. We know that the private sector is interested, and we hope to leverage all the interest in exploring space on our way to Mars. With innovation as the underpinning of the day, it was only appropriate that I have our next speaker here. I've heard a lot, since I have a couple of teenagers, that about 50% of the jobs that are going to be available to them in 20 years have not yet been invented. And I will argue that Tom Khalil has one of those jobs. His title, 2 of them, Deputy Director for Technology and Innovation at OSTP, and the Senior Advisor for Technology and Innovation for the National Economic Council. We would not be here without Tom Khalil. I would not be here without Tom Khalil. He and I shared an office on transition team. He was leading the transition for OSTP when I was leading it for NASA. Got to know him better then, knew him a little bit in the Clinton administration. And him being able to drive this in a way, both at OSTP and at the NEC, has allowed NASA to really gain its foothold within the White House to make sure that we have all the interest and attention that we know we need to move this forward. So, Tom, because of this, as I introduce you, I would like to present you with a piece of an asteroid. As I mentioned, lots of great science in the detection realm, but also here on Earth in the ground-based detection. We have a piece of Vesta, an asteroid that we know had a part that came in and entered the Earth's atmosphere and landed in Antarctica. I wish I could tell you I picked it up. This particular piece was picked up in 1995. We, through this research, know so much more about past impacts. We know that this asteroid itself is 4.5 billion years old. So, Mr. Innovation, that is not new, but you are making it absolutely critical to NASA and to the country, and the R&D efforts that we have are because of your support. So I am here to welcome Tom Khalil and present him with a piece of Vesta.
Thank you so much. So did you clear this with council? Well, Lori, thank you so much for that kind introduction. I want to start off by telling you a story. I told my 11-year-old son, John, that I was going to be giving a talk on asteroids this morning. And he said, no offense, Dad, which is what my children always say before they're about to totally diss me. He said, you don't know anything about asteroids. Why are you giving a talk on asteroids? And the reason is that I wanted to explain why this effort is so important and how it relates to President Obama's broader strategy for American innovation, with a particular focus on the grand challenge that Lori announced. First of all, it's incredibly important in its own right, and I think the late Congressman George Brown put it best when he said, if someday in the future we discover well in advance that an asteroid that's big enough to cause a mass extinction is going to hit the Earth, and we alter the course of that asteroid so it doesn't hit us, it will be one of the most important accomplishments in all of human history. And even if you're thinking about something that is less cataclysmic than that, given that we have already been able to detect a lot of the asteroids that are larger than a kilometer, recently 200 experts at the 2013 Planetary Defense Conference concluded that, quote, we've discovered only a small percentage of the objects that could destroy a city or cause severe regional destruction, and such an object could enter our atmosphere with little or no warning. So if we think not only about what happened recently in Russia or in 1908 when an asteroid that exploded over Siberia that was only 45 to 60 meters in diameter and still leveled trees in an area approximately 850 square miles, I think you get a sense for why dramatically improving our ability to detect and know what to do about near-Earth asteroids is very important. But thinking not only about asteroids as a threat, but also as a resource, I think is very important. And if we're going to extend the economic sphere of human civilization beyond the planet, then our ability to detect and characterize and eventually visit near-Earth asteroids is going to be a very important stepping stone in that effort. As Lori mentioned, the administration has made this mission one of the grand challenges, and grand challenges are ambitious but achievable goals that are going to require science, technology, and innovation to achieve, and that also have the ability to capture the public imagination. Some historical examples of grand challenges are obviously President Kennedy's decision to put a man on the moon, or the decision to sequence the Human Genome Project, which when we started was $100 million and is now rapidly approaching $1,000. More recently, the Department of Energy has launched several clean energy grand challenges, one called Sunshot, where the goal is to make solar as cheap as coal, and EV Everywhere, where the goal is to make electric vehicles as affordable and convenient to own as a gas-powered vehicle. In April, President Obama unveiled the BRAIN Initiative, which is an effort to dramatically improve our understanding of how the brain works. How do 80 billion neurons work together to produce memory, learning, perception, action, and consciousness, and ultimately establishing the foundation for improving our ability to detect and treat and ultimately to prevent diseases of the brain. But the president also issued a call to action. He said, not only is the government going to be pursuing these grand challenges, but we would also like to see companies and research universities and foundations and philanthropists and individuals get involved as well to identify and pursue some of these grand challenges. And already we've seen IBM drive advances in cognitive computing by beating Garry Kasparov at chess and Ken Jennings at Jeopardy, Qualcomm supporting a major incentive prize for a tricorder, Google building on an earlier DARPA grand challenge to develop self-driving cars that could reduce the number of traffic fatalities by 50%, and Elon Musk of SpaceX saying, I want to die on Mars, but not on impact. So those are all great examples of the private sector stepping up to the plate and identifying a really ambitious goal that they want to help achieve. Research universities are getting into the mix as well. So UCLA announced an effort to organize their next multi-billion-dollar capital campaign around a series of grand challenges. And I want to recognize the work of Kristen Dorgalow in OSTP, who's our very first assistant director for grand challenges. Now, one of the things that Lori mentioned is that the way in which we're going to achieve these grand challenges is not through the government operating in isolation, but really having efforts that are informed by Joy's law. Many people have heard of Moore's law. The number of transistors on an integrated circuit doubles every 12 to 18 months. Bill Joy was one of the co-founders of Sun Microsystems, and he said, no matter who you are, most of the smart people work for someone else. And the administration has been promoting a series of strategies for promoting innovation that are really based on that. So public-private partnerships under the Space Act, agreements where NASA acts as a catalyst for additional private sector co-investment. Citizen science, Lori mentioned, we've already seen the example of Fold It, which is a game that is teaching people how to solve one of the toughest problems in biology, which is protein folding. And in a matter of 3 weeks, citizens who were playing this game were able to solve the structure of an AIDS-related enzyme that the research community had been working on for 10 years. So what's really exciting is that I think citizens are going to be able to make contributions to solving these problems in ways that we haven't seen before. Incentive prizes. So this is another area where NASA has really been a leader. Under the right conditions, a well-designed prize can have a number of advantages relative to traditional grants and contracts. The government only pays if someone is successful. The government can establish a goal without deciding upfront which team is in the best position to achieve that goal or even what the right approach is, and the ability to really tap expertise from all over the country and all over the world from non-traditional sources. And obviously the international collaboration is going to be key in this area because the problem of near-Earth asteroids is not a uniquely American problem. But I think this effort is also important because it demonstrates a willingness to tackle a problem that is long-term in nature in a society that is often dominated by the 24-hour news cycle or the quarterly earnings reports or getting ready for the next election or responding to the next tweet. And I think it's very important that we have an increased capacity to work on long-term problems. And I'm reminded of a story that President Kennedy used to tell, in which he talked about a French general who asked his gardener to plant a tree, and the gardener objected that the tree was slow growing and would not reach maturity for 100 years. So the general replied, in that case, there's no time to lose. Plant it this afternoon. So let's get going today. Thank you very much.
Thank you, Tom and Lori, for kicking us off today and sharing some of those insightful insights into many of the different innovation mechanisms that have been used by government and also by NASA for quite some time to solve tough problems. NASA is not a stranger to using incentive prizes, citizen science, and open innovation for doing great things and advancing our mission. And this grand challenge gives us another great opportunity to apply those tools in an area of global importance. So we're really excited to be able to move forward with that. As Lori laid out at the beginning of the discussion today, the Asteroid Initiative is in two parts. So the Asteroid mission and the Grand Challenge. Right now, we will hear from a panel of esteemed senior leaders at NASA to talk a bit more about their perspectives on the asteroid mission portion of the Asteroid Initiative. There will also be time for questions after the panel. Now, keep in mind, folks in the room, that there will be two people with microphones, myself and someone on the other side of the room. Lauren will be running up and down the halls as well with microphone. For those of you that are connecting via social media or Ustream, make sure to tweet your questions to #AskNASA in order to be able to ask your question via social media as well. And with that, I'm going to give some quick introductions of our esteemed panel, a treat that we have this morning to hear from. We have first Robert Lightfoot, who is NASA's Associate Administrator, the agency's highest-ranking civil servant position. He previously was the director of NASA's Marshall Space Flight Center in Huntsville, Alabama, and he began his NASA career at the Marshall Center in 1989. Next, we have Dr. John M. Grunsfeld. He's the Associate Administrator for the Science Mission Directorate. You all probably know him better as the Hubble repairman. Dr. Grunsfeld joined NASA's astronaut office in 1992, and he's the veteran of 5 space shuttle flights and visited Hubble 3 times during these missions. You can follow him on Twitter at AskSciAstro. Next, we have Dr. Michael Gazarek, who is the Associate Administrator for NASA's newest mission directorate, the Space Technology Mission Directorate. Dr. Gazarek has over 25 years of experience in the design, development, and deployment of spaceflight systems. You can follow NASA's Space Technology Mission Directorate at NASA Technology on Twitter. And finally, we have William Gerstenmaier, who's the Associate Administrator for the Human Exploration and Operations Directorate. Previously, he served as the manager of the International Space Station program. He began his NASA career in 1977 at the then Lewis Research Center in Cleveland, Ohio. Please welcome, join me in welcoming these men to the panel.
Okay, well, thanks, Jen. I appreciate you giving us that introduction, and thank you all for being here today. This is a pretty exciting day for us. We get to share with you the process we've gone through to get to this point with this mission. We really believe we've got a pretty integrated strategy here between the 3 mission directorates, which is somewhat unprecedented here from our perspective of integrating 3 of our top line items for the agency. So what I'm going to do is walk through an overview here real quick, and then I'm going to turn it over to each one of these to share their perspective on their individual segments as we go. So if I can get the next chart, please. So this is kind of the alignment strategy that we've been looking at. We're talking about 3 different segments of this mission, and the top piece is the identification segment. You can see that we'll spend some time between now and 2016 working on identifying, characterizing, and choosing a candidate asteroid for us to go capture. The second piece is a redirect segment. This is a segment that's most notional at this point in that it's the conceptual piece of where we're headed. This is the part where we'll pull together what Mike Gazarek and his team in space technology are working on for solar electric propulsion, but the capture technique that we'll pull together as well to actually go out to get the asteroid and bring it back into translunar space for a stable orbit that we can then go for the last segment, which is the exploration piece of this segment, where we'll take SLS and Orion and go visit the asteroid and as early as the 2021 timeframe, depending on where we pick an asteroid. So that's kind of how these all line up from a segment perspective in these 3 pieces. We think it's pretty integrated, and as you're going to hear from each one of these, these are activities we're already doing. These are things that we're already working on, and just being able to integrate them is pretty important. If you go to the next chart, please. So this kind of lays out those 3 pieces in a pretty simple way. Identify. John's going to talk about that. He's going to walk you through what we're doing and what the FY14 budget does to provide more information on the identification part of this. The second segment, of course, is redirect, and Mike's going to walk through solar electric propulsion, and Gerst is going to walk through some of the capture techniques we're looking at. And then the exploration piece, Gerst will walk through the Orion SLS piece of this puzzle as we go forward. So we'll have plenty of time at the end for questions and answers, and I think I come in at the end and give you our path forward to the mission formulation review that we'll be doing at the end of July. So with that, we'll turn it over to John.
Thanks very much, Robert. Of course, being the science guy, the first thing that I want to talk about briefly is, why are we interested in asteroids? And if we could start the slides. Asteroids are something that Lori Garver talked about as a threat to Earth, but they're actually incredibly interesting from a scientific viewpoint as well. Next slide. And here you see what is an artist's rendition of an early solar system. And one of the things that we've learned from our astrophysics missions and our planetary science is that when solar systems form, when the cloud of gas from which our solar system formed comes together, that planets and bits of planets, planetesimals, form almost at the same time as the star. And so these asteroids are the results of collisions of planets that never formed, really are primordial in the sense that they are the stuff that the Earth was made out of, that the solar system's made out of. And there's actually a little animation running that shows you a model of a solar system forming, a planet forming around a star. The star's actually not turned on there. It's the dark spot in the middle. And it shows gaps opening up and planets forming. And in some of those gaps are leftover pieces, just like any construction project. You have lots of bits left over. And those are the asteroids. So they give us a sample of the primordial material. And sort of notionally shown in the bottom, are some pictures of comets and asteroids. Some asteroids may be dead comets. And we've been studying these for a long time. In fact, folks have been identifying asteroids, for hundreds of years, if not thousands of years. We were thrilled to give Tom Khalil a piece of Vesta. We know that because we've studied Vesta now in great detail, and the piece that we gave to the White House today has the same characteristics as Vesta, and Vesta is a little bit unique. But we see asteroids that are made of iron and nickel, that would be at the core of a planet, for instance, like Earth, but also some asteroids that have a lot of water, some asteroids that have a lot of organic materials. And in the next slide, you'll see kind of a family portrait, not pictures from hundreds of years ago, or actually Vesta, which you can see with your naked eye if it's close enough, but asteroids that we've actually gone to visit and take pictures of. These asteroids are relatively large for the most part, tens, hundreds of kilometers across, and it shows you kind of the variety, and they look a little bit beaten up. And that's because these asteroids have been around for billions of years, and they do collide. We see many asteroids that have moonlets. Some of them may be from even recent collisions. And we have the main asteroid belt, of course, between Mars and Jupiter, where collisions happen frequently, sometimes knocking stuff into the inner solar system, which we see go zipping by. And so these are our samples of the material from which the solar system formed. If you hit the next, you'll see a very small one there, which is going to zoom in. It's really not so small. It's hundreds of meters, 500 meters across. And this is Itokawa, which we went and visited. And you'll see that it looks like a collection of stones. These are actually huge boulders, all stuck together with a lot of dust. And this looks like two asteroids which have collided and eventually merged into one. And this is an example of a potentially hazardous asteroid that orbits similar to Earth that we've studied in some detail. I also told my kids that I was going to come today and talk about asteroids. And on Father's Day, my daughter gave me actually a piece of a Palisite asteroid, which I have as a prop. Science guys like props. And this is an iron nickel and olivine. It's a mineral, very, very common in early asteroids. This was from a 1,500 kilogram asteroid that landed in Argentina. Probably nobody was around to see it then. Maybe the dinosaurs were. It was excavated on a farm. And so my daughter's also very interested in asteroids. So this is something that we've been studying in science for a long time. Next slide. So how do we find them? Well, we use observatories. We don't need particularly large telescopes, but not insignificant. We use the Catalina Sky Survey, the MIT Linear Telescope, a telescope called Pan-STARRS. And these are telescopes that are a couple of meters across, and they scan the sky at night. And so what you see in the middle are stars. They're fixed as the telescope tracks the night sky. And hopefully you saw a small object moving across the sky. Here it is. And we then identify that as a moving object. We follow it up, and this was then determined to be an asteroid. These are then cataloged. We sponsor the Minor Planet Center at Harvard-Smithsonian Center for Astrophysics, Harvard-Smithsonian Observatory, and the Jet Propulsion Lab through our Near-Earth Object Observation Program at the Jet Propulsion Lab. So this is one way that we identify them. Next slide. We also use radars. Once we've identified one, we want to characterize it. When some of these come near enough to the Earth, we can use the Goldstone radar to ping off of it. That gives us surface characteristics, and eventually we can build up a map. of the surface of the object and determine its rotation rate. An example is one that's got the telephone numbers 1999 RQ36. It's been renamed Bennu, and this is going to be the target of the OSIRIS-REx mission. So in 2016, NASA is launching a mission from the Science Mission Directorate. Dante Laurento is the principal investigator at University of Arizona. We're going to send a mission out to an asteroid. It's going to orbit it, characterize it down to very small scales, millimeter scales, and then it's going to do a touch and go and bring back a sample in 2022 from Bennu. And these are our radar observations. We also use the Arecibo Observatory in Puerto Rico. Next slide. So how are we doing on finding all of these asteroids and potentially hazardous asteroids? Well, since 1998, when we really kicked up the game on our study program, we've identified many, many asteroids, and it shows down there on your right, on your left, the plot of the identification versus time, and you can see how that spikes up starting around 1998, and that plot shows two different types: very large near-Earth asteroids and all near-Earth asteroids. If you want to know how complete is it, we have a model of what the size distribution of asteroids look like. Based on that model, we can say that we've found greater than 90% of all asteroids greater than a kilometer. Between 300 meters and a kilometer, 60%, and it decreases from there. Part of the reason why we can't see the smaller asteroids is we don't have the capability to do so, and part of it's nature. We can only see these small asteroids when they come close enough to the Earth to be bright enough for us to detect. Another part of it is that the smaller the object, its orbit changes over time. And so maybe we see it once, but we can't confirm it because the next time it comes around, it's in a slightly different orbit. So there's a lot of challenges that nature presents. And these are some of the challenges we hope to solve in the future. Next slide. So how do we hope to do that? We're going to increase, with this proposal in the FY14 President's budget, to increase the study rate with the pan-stars. We're also hoping to reactivate the Wide Field Spectroscopic Explorer WISE, which was turned into NEO-WISE, Near Earth Observatory WISE. Bring that back to life. It's dormant right now. And also the Space Surveillance Telescope in partnership with the United States Air Force. Once we find an object, we can characterize it. NASA has an infrared telescope facility on Mauna Kea, also the Spitzer Space Telescope and other assets. But that's not all. Fortunately, asteroids are something that actually you can study with a rather large backyard telescope, and many amateurs and many communities have those telescopes. Next slide. And so we want to engage what we have called citizen science, which is really just amateur astronomers and pro-am astronomers who like to go out in their backyard at night and detect, characterize through light curves, discover new asteroids. And we also share data, for instance, pan-stars data with the ISACS project, which is a consortium of universities that provide astronomical data from these large telescopes to amateurs to study. And quite a large number of asteroids have actually been discovered or rediscovered and characterized by high school students. And there's one shown on the left who's a local Virginia student who won an American Institute of Aeronautics and Astronautics science fair project by discovering with his partners a number of asteroids and characterizing some others. So that's sort of the why and the how, and I'll turn it over to Mike Gazarek to talk about the technology that we'll use.
Thanks, John. Well, I didn't bring an example of high-power solar electric propulsion with me today, which is probably good for all of us. But let me talk about that if I can have the next slide. And let me talk a little bit about space technology and the technologies that we're working on. And again, we can have the next slide. So just a brief context setting. We know to explore deep space, and this is what this mission is an example of, we need a number of technologies. These are not new. In fact, many of you in this room I know have worked on many reports over 30 years talking about the technologies we need to explore deep space. And they come in a variety of challenges. They're listed here. Today, of course, I want to focus on propulsion, in particular, high-power solar electric propulsion. So let's go to the next chart. Solar electric propulsion is not new. It's been around for a number of years, starting with Deep Space One, again, a science mission using solar electric propulsion to navigate and move through the solar system. And then particularly Dawn, as we had examples of it today, of visiting the asteroids that it's going to, using, again, was a really novel use of solar electric propulsion. In fact, there was a number of technology developments prior to that mission that really enabled the use of Dawn to use solar electric propulsion. Well, since that point in time, solar electric propulsion now is used by industry for commercial spacecraft. In fact, Boeing has an all-electric spacecraft. But in particular, on this chart, the AEHF satellite, many of you may have followed in the news. The upper stage didn't quite work out as well. It couldn't get to its orbit. And they used a very novel application of the solar electric thrusters that are on board that spacecraft to get it into its orbit. This is a multi-billion-dollar satellite that would have been lost had it not been for the use, the knowledge, the technology for solar electric propulsion. And so that's really where we are today. The next step, high power. For not only NASA to do this mission it's called the 50 kilowatt range, but also for future missions. Coming out of architecture studies, and again, there are many of them, high power solar electric propulsion, the ability to move cargo to destinations that we intend to go, right, is an enabler, an incredibly mass saver in terms of getting the infrastructure that we need to explore the solar system. That is not new. And it is time, after many years of reports, to go invest in this technology. Industry has come to us and said multiple times, there's risk involved at the high power level. Can the government address those risks, enabling a whole host of opportunities that I'll talk to in a minute? It's not only NASA. The House Armed Services Committee, just in a recent report, recommended that the Air Force get together with NRO and NASA to get together and look at the investments in technology for high power solar electric propulsion. Let's go to the next chart. Today, when we look at solar electric propulsion, we break it down into these three main subsystems. And I won't go through you into details, although I love to, being the tech guy. But the main components are solar arrays, the ability to collect the sun's energy that we need, right, to turn into propulsion. The electronics and the thrusters, kind of the sexy part of this. And then the propellant system to store the material, the xenon that we use for propulsion. It turns out, if you look at high power today, the real trick, the real long pole in the tent is in the arrays. We just can't collect enough energy. We need larger arrays. And if you need larger arrays that have to fit in today's rocket shrouds, they have to be deployable. They have to be able to fold up. We are pushing on packaging densities and power per mass ratios, factors of 2, 4, even up to 6 times what's over the state of the art today. We need these large arrays. They have to unfurl, and they need to be able to pack into the volume of the shroud. And that's where we have investments already started today in space technology in these large-scale solar arrays. If we go to the next chart. So as I mentioned before, high-power solar electric is not only for this mission that we're talking about today, but it's also for a whole host of applications, both industrial and other government agencies, and with our international partners. This is high-power solar electric is called out by the NRC, one of the tipping point technologies, right, that enables a whole host of applications, including not only human exploration, as we discussed, satellite servicing. We talked about payload delivery and the ability, for example, to rescue AEHF, to get us to its orbit, use on station, future robotic missions above and beyond what we see on Dawn, orbital debris removal, and other applications as shown there. So high power solar electric propulsion is a technology that's needed by many. It's needed by NASA. It is time to develop it. And that's what we do in space tech. We develop technology with a purpose, and this is just a great example of that. So that's where we are for solar electric propulsion. I'm going to now turn it over to Bill. We'll hear more about the mission and hear more about the RFI.
Thanks, Mike. If I can have my next slide, please. As John talked about, he described the observation, the identified piece. Then Mike talked a little bit about the electric propulsion and some of the technology. What I'll talk about now is a little bit the redirect mission itself, and then I'll talk about how that mission fits into our overall human exploration plans going forward in the future. So next slide. So this is the asteroid redirect segment reference concept that we've put together. Basically what we're going to do is we're going to capture and redirect a 7 to 10 meter, approximately 500-ton near-Earth asteroid to a stable orbit in translunar space, probably a deep retrograde orbit around the moon. And this will enable an astronaut mission to the asteroid as early as 2021, around the time of the EM2 mission that we've currently planned with Orion and SLS. And we see this as a forward and kind of parallel approach. In other words, we'll be doing some of the observations that John described earlier at the same time we're actually building the hardware for the mission. So we won't fully have identified the target we're going to go to when we potentially, while we're actually building the spacecraft. So we'll build the spacecraft and a capture device to a set of generic capabilities, a generic set of specifications, and then once we finally identified the target that we really want to go to grab onto and redirect, then we'll go launch in that direction. Next chart. So a little bit about what this involves. We took essentially a candidate target 2009 BD. We took a look at what it would take to actually put this mission together, and you can see on your left the trajectory to the asteroid. You can see it takes about 1.84 years to get there. That's a function of what launch vehicle it comes off of. If it comes off of an SLS or a Falcon 9 Heavy or a Delta IV with lots of essentially initial thrust, then the transit time is about what you see on this chart. If we take a smaller rocket and launch with that, then we'll spiral out using electric propulsion, and that will take significantly longer to get out to the object. But you can see that it's not trivial to get out there. It's the 671 days time of flight out to get out to the object. Then we essentially attach to the object in the picture on the right, and then we essentially redirect, and we say redirect rather than to bring back, and we say that purposely because the object is already in an orbit that brings it back to the vicinity of the moon and the Earth. So we take advantage of the fact it's already coming back, so we don't have to change velocity in that direction. All we need to do is essentially redirect it such we can use the Earth's gravity, use the lunar gravity to add some more delta velocity to this object in the spacecraft, and then we can put it into a deep retrograde orbit around the moon. And that orbit is intriguing because it's essentially stable with no propellant, no attitude control, no orbital maintenance for up to maybe 100 years. So once we get the spacecraft and the object in this orbit, it's there for us to go visit multiple times in the future. And again, this is kind of our reference concept. Again, I would take these, this is just a target we picked just to make sure from a feasibility standpoint this could work and make sure we understand the delta velocities, et cetera. Next chart. We're also looking at some alternatives. Maybe there's some different techniques that may be good to go look at. We're requesting these ideas through this RFI that's been released. One additional concept study is to take a look at maybe go out to a larger near-Earth asteroid. John showed you a picture of one of the objects that was very large with a large number of boulders on the surface of it. So maybe instead of going out to a small asteroid, which are tough to track for the reasons that John described earlier, maybe we go to a large asteroid, a couple hundred kilometers potentially, maybe tens of kilometers, and then we can actually then maybe push on that object, see if we can put a delta velocity change in it on the order of millimeters per second, extremely small change in delta velocity. But that small velocity applied early enough could be the velocity that deflects this object away from the Earth. And we could actually then prove that the concept of actually pushing on one of these large objects is actually effective and actually works. Then we would come off the object, we would go survey it, find a boulder that looks appropriate for the capture device we have, and then grab that boulder off the surface and then do the same redirect that I described earlier. So this is one thing we've been thinking about, and we're looking for other ideas as you comment to the RFI. Think of other ways we can make these ties more real to other objectives, other programs with us. We look to the creativity that you have here in this audience to help us figure out ways to do this in a slightly different manner. The other thing you'll notice on here is that when we do this, because we spent a significant amount of delta velocity pushing on this large object, the size of the object we can bring back is now smaller. So you can see on this chart we'd bring back something on the order of 1 to 10 meters. So we recognize that when we redirect or bring this object back into this deep retrograde orbit, it'll be smaller in this case. But it gives you essentially a real-world example of pushing on a larger object. Next. Again, a little bit more about the mission in picture form here. You can see this is the crewed mission portion where we would use the SLS to launch the crew out to this deep retrograde orbit. We can do that with no changes to the SLS vehicle. Its initial configuration, the 70 metric ton SLS, works fine in this capability. The Orion spacecraft is compatible with this mission. It was designed to have spacewalks out of the Orion capsule, so we can go do a spacewalk out of the capsule. The basic stay time in this deep retrograde orbit is compatible with what we wanted to go do. So it essentially fits right with what we were doing already. So as we described earlier, this whole mission activity captures a lot what we were doing before. It captures the observation things that John was working on. It captures the electric propulsion that Mike was working on. And it captures and utilizes our Orion and SLS just as it was envisioned. So in a very nice sense, it ties the three directorates very closely together into a nice integrated mission that gives us a pretty interesting thing to do in deep space. Next. This is what the profile or the rendezvous looks like with Orion out to this object. You can see we leave Earth and we do a lunar gravity assist around the moon to end up in this retrograde orbit. We'll essentially stay in this deep retrograde orbit for roughly 5 days. During that time, we believe we can do 2 spacewalks out of the Orion, and those would be about 4 hours duration each. And that allows us to do fairly simple spacewalks to go out to grab a piece of the asteroid to then be returned in the Orion capsule as it comes back. The good thing about this is it's actually given us an experience of operating in deep space. It's allowing us on the human side to start using lunar gravity assist, which we think is an important tool to us to get to these regions. And it also puts us in a situation where once we're out on this deep retrograde orbit, we're committed to be there for 3 or 4 days before we can actually get the crew back to the Earth. So this gives us some experience of operating in a different regime than where we operate today with Space Station. In the case of Space Station, if the crew has a problem or the spacecraft has a problem, we can be home in a matter of hours. In this case, we're going to have to make sure we have the right abort scenarios, the right redundancy in place that we can tolerate being in this situation for up to 5 days. So that helps us take a step towards the bigger missions that we want to do going forward. Next chart. Again, this is a little more detail on the spacewalk. And again, in the RFI, we're asking for some suggestions for you on other ways we might do this. We show conceptually what we would do. You'll notice here we didn't dock to the robotic spacecraft. We used a little robotic arm. That arm is designed the concept is off of the Robonaut that's on board Space Station. So we're repurposing, again, components we have in other areas to be used there. We'll look to you to give us other ideas and suggestions on how we ought to do this. You see us using a Strela kind of boom, a Russian type of boom, or to get over to the robotic spacecraft and then to get out to the asteroid itself. Again, we're looking for ideas and concepts from you about better ways to do this, more efficient ways, things that will actually feed forward to other missions we'll want to do in exploration, want to do in deep space. So we look to you to take the vision of this is one mission, but it's really that first step that's going to allow us to get humans beyond low Earth orbit, to push further out into the universe. And we look for you to help us figure out ways to connect those dots to make effective use of this mission so it feeds forward to those other bigger destinations and things we want to go do. Next. This is the capability-driven framework, kind of what I was alluding to before. We see this where we do things on Space Station today. It's a very good microgravity platform. It's excellent for us to learn about astronaut health for long durations in space. It's also good to check out spacesuits. We'll use the spacesuits for this mission on the ISS probably initially, so it's there. It's a tremendous research facility. It's kind of our first foothold in low Earth orbit. Then you're going to see us move out beyond low Earth orbit. This region around the moon is very intriguing to us. This deep retrograde orbit is interesting. It provides some neat things for us to get a chance to not only be there to pick up this sample, but we can also observe the moon, and we can see some things on the other side of the moon which we would not typically get from other orbits. We can also transition from this orbit to Lagrangian points. We can maneuver around to low lunar orbit, etc. So this is, again, a stepping stone that gives us experience, gains us knowledge as we move forward. And our ultimate goal is to get to Mars, and you can see each one of these steps as you move further and further out requires more and more capability for us, both from a technology standpoint, but also in just an operational preparedness standpoint. Next. One thing I think that's important is that this mission is a mission itself, but it also ties directly into the long-term human Mars exploration strategy. Again, we're using the Orion vehicle, the SLS vehicle. We get this electric propulsion capability, which we think has tremendous potential for us. This mission would not be possible if we didn't have electric propulsion. The amount of delta velocity that we need to impart to even redirect this asteroid would not be possible with chemical propulsion. It requires electric propulsion. As we position cargo for Mars missions and those kind of classes of missions, we're going to clearly want to use the same type of electric propulsion, so it fits as we move forward. I talked about operations and risk management. We think that's important. Communications, to understand operating in not a perfect communications environment. We're going to have to do that as we push out. We'll also get a chance to look at sample acquisition, caching, storing operations that will fit as we go forward. We also get to work and interact with the planetary body, which we think is also tremendously important as we start getting ready to go out to the moon, or go out to Mars, or go out to potentially a moon of Mars. Those same kind of things that we're doing with this robotic spacecraft and this sample fit, and they all move forward. So this is a great mission that keeps us moving forward, keeps pushing human exploration in the right direction. Next. So this is another graphic kind of the way we see us advancing from where we are today with the International Space Station. You can see on here the transit times. You know, we're essentially maybe 2 days on space station away, actually hours. Moon is 3 to 7 days, depending on where we're going. The Lagrangian points are a little bit further. And then obviously Mars is this 6 to 9 month kind of activity, which is a pretty demanding thing. So the idea is to really build the technology, build the operational concepts, build the hardware that allow us to continue to keep pushing out. Next. And so again, what we're asking for you today is, the request for information is out there. We're asking for you to think about concepts and different approaches than maybe what we've described here. We've given you some reference ideas. We've given you one permutation of that reference idea, but we want you to think about other ways of enhancing this to get the most out of it. So we're looking for things on asteroid observation that John can use to improve that activity. We're looking for some redirection systems discussions that might fit into Mike's area. Some deflection demonstrations, do those make sense? How can we increase our learning from that? Asteroid capture systems, those are going to be unique to capture this device and to despin it. We need some help in understanding those, some crew systems, and then partnerships and participatory engagement. We're looking for all these comments to these things to help us get a better system. And this RFI is open to all organizations, including industry, universities, nonprofit organizations, NASA centers, FFRDCs, and other government agencies and international organizations. So I don't think there's anybody else I could put down at the bottom. I think we've included everybody. And so we're looking for your comments and we're looking for your suggestions. Next. And I think Robert's got one chart that'll be coming up here somewhere.
Yeah. So what I thought I'd do is so how does all this come together? At what point? How do we pull that together? So if I can get the next chart, as soon as it comes up, what we're gonna do now is we're gonna start taking the information today. Today is a pretty important day for us to get all you engaged and start to get your thoughts into our planning. We have, as Gerst talked about, we've got a lot of information that we want to get from the RFI. We'll see how that works, and that release comes out today. We've got the Target Neo 2 workshop coming up in July. It's another opportunity for us to engage with the Small Bodies Assessment Group and get some ideas from that area as well, and talk about some of the challenges, as John discussed again, with the identification and characterization of these smaller asteroids that we've got to go deal with. We're looking for a pretty interactive process between now and July 18th, when we expect the response from everybody on the RFI. July 30th is our internal mission formulation review, and this is going to be specifically related to the design reference mission that Gerst talked about a minute ago. That mission, we're going to look at what's the pursuit of the overall mission. We're going to look for mission success criteria. We're going to look for what kind of content do we need to put into our budget process as we move forward with our budget cycle. We still have that to do as well as we move forward. Content, structure, center participation, where's the right expertise located within the agency. So far it's been a tremendous multi-center team that's been pulling this together. And we really do. We're getting the best folks working on this in the agency, and we got to start talking about that. Talk about our make or buy planning. This is a pretty important step for us in terms of, is this something that we can buy, depending on what the pieces are. We'll do that in July. In September, we'll kind of bring it all together. We will have finished the mission formulation review. We'll be getting the responses in from the RFI, and we'll be able to kind of piece it all together and start going down the path toward what is a more traditional mission concept review, so that we can see where we can add pieces in that you guys have brought forward. We can piece together what we've learned with the mission formulation review. And so that September timeframe is going to be really important for us for kind of really tying down what the mission is going to look like, what alternatives we still want to pursue, what areas we want to go after, and also starting to get some more refined input into the budget process. So a pretty busy next 3 months for us as we get going, and that'll all lead toward a mission concept review, probably somewhere around the first of the year is when we'll start getting into that arena. So that's the path forward, and appreciate what these guys have shared with you. They've done a good job kind of laying out what we've been working on for the last couple of months, actually for several years, actually. I think the last couple of months we've just kind of got it to coalesce. So at that point, Jen, whenever you guys are ready.
Let's give these guys a round of applause, please. So now we have some time for questions. I'm going to give some instructions about how we're going to take questions both from the audience and for those that are participating virtually on Twitter. For those of you that are in the audience, you need to try to flag me down on this side or Lauren Worley if you'll raise your hand on the other side, flag her down. We'll start in the audience on my side with a question, and then we'll go over to Lauren and vice versa. We'll also be taking some questions from social media. Now keep in mind, folks that are on social media, to tag your questions on Twitter with the hashtag AskNASA hashtag in order for them to be able to see it. And when you're asking the question, we do also ask that you note who you'd like to answer the question, who the question is for, and try to ask one person so we can get to as many questions as possible. So I'll go ahead and start on this side.
Hi, this is Chris Lewicki, President of Planetary Resources. I think this question is for Dr. Grunsfeld. It's interesting to see all this come together today after the announcement a few months ago. In addition to orbital mechanics and things that factor in for timelines, I'm interested to hear how composition of a potential asteroid or a redirect object may factor into the decision for what we choose to go after for planetary defense, for science, for expanding human destinations, and for resources.
Well, composition is very important, but it kind of depends on what mission we end up actually executing. Composition is important from a science perspective. From a pure science perspective, we're most interested in carbonaceous objects that have a lot of primordial carbon in them, or primordial water. There are various theories for how did the stuff that we're made out of get onto the surface of the Earth. And one theory posits that after the object that collided with the Earth that created the Moon, and the Earth sort of started cooling, that there were a lot of other objects flying around the solar system, many of which seeded the Earth with even the basic amino acids from which life got its hold. And then, of course, now we're here worrying about other asteroids hitting us. And so those high carbon content asteroids are very interesting. But at the same time that the solar system was forming, there was a lot of water in the solar system. We formed in an area where liquid water can exist on a surface. And of course, that's advantageous for us, one of the key characteristics for life. But many asteroids then have potentially ices in them or minerals that are hydrated that have a high water content. From a planetary resources perspective, you could use that water as a resource both to drink or to create rocket fuel, hydrogen and oxygen. And there may be other resources. The particular meteorite that I have in my pocket is from an iron-nickel meteorite that has a lot of rare earth elements that could be used. But from a practical perspective, we're probably going to be looking at an object that has a lower density than an iron-nickel, probably a stony meteorite, and hopefully one with a high carbon or water content. And so those are the kind of things that we need to know before we go after a target, in addition just to the orbital mechanics. If we can't get it back to Earth, it's not that interesting. And so you start adding these selection factors, and it becomes a very narrow space. In fact, at the moment, I can't say with great confidence we have any targets. But that's the purpose of trying to engage more people and trying to enhance our detection capability.
Hi, my name is Rick DeWitt. I'm an independent mad scientist outside of any organization or institution. My question has to do with an observation that every asteroid that we've looked at has dust regolith sitting on the surface. And all three of you are affected by this because it's something we really haven't looked at very much. We want to look at it. So the question is it a mission objective to disturb that surface regolith as you bring it back into lunar orbit before the astronauts get to take a look at it? Thank you.
Well, I'll just give an example that OSIRIS-REx, which is the robotic mission to go out to this large asteroid Bennu, study it, and then do this touch and go where it will not quite land, but it'll come and be in contact with the surface, grab some samples, and come back, is depending on the fact that the surface is somewhat loose and unconsolidated. And so its plan is to disturb the dust and pebbles and rocks to push them off the surface where it'll grab them and bring them back. So from just a science collection viewpoint, it's depending on that, and our observations show that these objects are very much like that. I think from a technical viewpoint, disturbing the dust provides challenges.
I'm asking you in terms of the redirect mission.
Again, I think it's going to be pretty important to understand what this dust composition is, and the other problem is really characterizing this asteroid ahead of time. You know, we'll do as good as we can with the assets that John showed earlier, but we're not going to know with 100% certainty exactly what the composition is. We'll have maybe a good idea. We'll understand the spin rate, but we may not know the composition. So we're going to learn a lot about what the surface of this object is. Does it affect your ability to redirect, right? When you actually, as I described to you earlier, if we go to the bigger object in the alternate concept, if we try to push on it, right? Now we say we kick up some dust. Does that affect the efficiency of the solar electric propulsion? Does it cause some shorting between the cathode and anode that negates some of that? We don't know. So there's going to be some real learning here. We're not going to have everything answered when we go do this mission. And when that one little statement said forward leaning, right, and parallel, that's code words to us that we're not guaranteeing 100% success, but we're going to learn some things that are truly unique that will definitely help us with planetary protection. It'll help us with resource utilization. It'll really help us understand what these bodies are and how we can use them in the future. And that's more important to us than actually doing everything I described perfectly the way on those charts. I guarantee you will be surprised. I guarantee you will learn some new stuff, and that's what we're about.
Great. So we're going to go ahead and take one more question from the audience over here before taking a social media question, and then we'll go ahead to the other side of the room again.
Hi, David Gump with Deep Space Industries. A question, I think, for Mr. Gerstenmaier. One of the important long-term benefits of asteroids would be providing propellant for getting to Mars faster and cheaper, and that probably will be done on an industrial basis. What's your plan for involving industry at the beginning of this process so that the technology that gets developed is appropriate for long-term use?
And again, I would suggest the RFI we put out really opens that up to you right at the very beginning. So you ought to look at this from your perspective, and if you see potential industrial uses where we could use an asteroid as a propellant source for in situ resource utilization and those things, how can we affect the mission to actually maybe benefit more in that direction? So you should look at this RFI as your chance to tell us how you would like us to shape this mission, shape this activity that actually helps you going forward in terms of propellant generation or other things. So we're really opening this up to this large group for all of you to take a look at this, look at it from your perspective, and give us some ideas of how we can make the maximum benefit about what we're doing or getting ready to go do. And we'll shape the mission to try to capture the largest space we can to keep us moving forward. Because I think this is an important resource from a materials standpoint that we're going to have to, as we break our tie with the planet, I talked about it in terms of time, it's also materials. We're going to have to use the materials in space if we're going to continue to move further and further out from the Earth. And to do that, we're going to have to maximize that learning now, and I believe this activity is one way we can start to do that.
Yeah, and if I could add to that too, let me just add, we talked about this RFI and alternative systems and alternative propulsion systems. I just wanted to highlight that as well. I showed the kind of the baseline concept we have using Hall thrusters, again leveraging incredible development by industry over these past couple decades. But this RFI also opens it up to other advanced systems like magnetoplasma type systems. We're going to go look at those. We have a baseline concept, but in this RFI, we're going to ask and we're going to go look at other systems as well.
Great, thank you. And a lot of folks have been asking online where they can find this RFI.
So
You'll be able to find the RFI at nasa.gov/asteroid initiative starting at 11:30 today after the event is over. So please look for the RFI at that location. Now we're going to move to a question from social media, and Sarah Becky Ramsey from the Office of Communications will share with us what that question is.
We do indeed have a question. Prospect Dynamics asks, What's the best way for an early stage small business to engage this initiative for any of you?
Well, I think I'll take that one. I mean, this is why we're doing the RFI. I mean, this is exactly why we're doing it. I would say this is different for even us. This is why when you guys are asking us these very detailed questions and we don't have a very specific answer, we want to hear what you've got so we can factor that in. I mean, this is when you read the RFI, you'll see that you have an opportunity to submit any idea you want. What we want to be able to do is take the complete set of those ideas and kind of, I don't know, down select and somehow figure out a way to make the best mission that engages the most folks and brings the most ideas to the table. Too often, I think in the past for us, we come in, you know, it's already baked, it's already done, and people say, man, I had this idea, and sometimes we can be too late. It'll be too late for us to engage, to interject that into the mission planning. What we're saying here and what Bill and Mike are saying is, this is your chance to tell us some things. We may not be able to accept it all, but I'd rather know about it, right? And make a conscious decision. I call it eyes wide open. Make that conscious decision instead of hear about it after the fact and go, wow, we had a great idea, but nobody listened to us. This is your opportunity, and that's I think, the best way to engage here.
Hi, I'm David Morrison from NASA Ames, and the question is for Dr. Grunsfeld primarily, and that is, how do you intend to bring the scientific advisory structure into play in issues such as the type of asteroid, the need for precursor missions? Do you intend to go to the National Academy or to use NASA's own scientific advisory processes?
So, you know, one thing that Robert just mentioned is, you know, the RFI is open to everyone. That includes scientists. We're people too, occasionally. But specifically, and I think it was on the timeline, the Small Bodies Assessment Group, which is part of our advisory structure and analysis group, we're engaging them, and that's also part of the NEO2 workshop, which is primarily scientists, but scientists and engineers getting together. And that's the start of what will be a much longer dialogue with the scientific community.
Hi, my name is James Wanga, and I got involved in the Asteroid Initiative after a team that I was a part of in the New York Space Apps Challenge hackathon built a CubeSat analog out of a drone. The community outreach involved that NASA, like what happened during that hackathon, the way NASA reached out to the to the hackers and to the community, got a lot of people really excited about how we could get involved, and got a lot of people who were previously not interested in space and not interested in things like the Asteroid Initiative interested. Do you plan, as this goes forward, to engage the non-scientific community, the mad scientists of the world, and you know, in a non-official way, because it's hard for people like me to hear about things like RFIs, right? Because we're not involved in the industry. We're just mostly software engineers and teachers and students who don't know that much about what happens behind the scenes. So,
I think the best way for that is Jason Kessler's going to get up and talk in a minute about how some of the other ways to engage other than the request for information that we're going to put out. So when he talks, if you don't get your question answered, then ask him, because we have a great plan associated with exactly what you're talking about, crowdsourcing and things like that, where we can bring folks in. And Jason will discuss that in a minute.
And we'll take one more question on this side and then move to another social media question before coming back over here.
Mike Hilton, retired aerospace engineer, emphasis on retired. Question for Bill, and I assume retired aerospace engineers are also in the RFI list that you gave. Okay.
Couple of human beings. So
human beings.
If you fit, you're there.
A couple of comments. You might consider using the asteroid capture device in Earth orbit to capture some space debris or even some bags of junk thrown out by the space station, just to test it, to see how it works and make adjustments before actually using it on an asteroid in the long-term long trip that's required. Second comment is you might want to consider bringing the asteroid back in high Earth orbit instead of lunar orbit, since there you could get to and from it a lot faster, and maybe even set up a lab on the asteroid or use the asteroid as a lab, as a second space station, to do a lot of testing on how to use the asteroid for different resources and fuel and so forth. So I haven't heard that much, and you may have considered that already, but I would suggest to look at that.
Okay. Those are good comments that we would expect to see in the RFI. So those are excellent thoughts.
All right, we'll go ahead and take another question from social media.
All right, we have a question about the RFI. The theme of today is citizen science, but your list says that organizations can respond to the RFI. Can individuals also submit ideas?
Absolutely.
All right, no, we have another question back here.
Yeah, hi, Dave Murrow from Lockheed Martin. Just a kind of a simple question about timing. You showed in your alignment chart the Asteroid mission coming back in 2021 or something like that, and as early as, I think you said. What are the realistic timeframes for targets to come back, the ones that you found and the ones that you expect to find, and what will you do if, say, 2025 might be the earliest that we could go visit it with a human spacecraft?
Yeah, again, we kind of see these activities as not being all tightly connected. So in other words, if we find an object that naturally returns, as I described earlier, we can't put enough delta velocity in to really change the arrival time. So we have to find an object that's coming back into the Earth-Moon system naturally on its own, and then we just deflect it. So there very well could be some objects in the 2023, 2025 timeframe that are there. You know, it's going to be hard to find an object that meets all these criteria, right? It's got to be a certain size, a certain composition, depending on how much scientific stuff we want, as well as the orbital mechanics constraints, spin rate. It's going to be tough to find one of these, so we'll pick that date. But then that doesn't hold up the entire human spaceflight program. We're still going to continue with Orion with our test flight. You know, first of all, just the capsule test flight in 2014, and then the uncrewed mission in 2017, and then our 2021 flight there, and then we'll be ready to go with this other mission. In fact, if you think about it logically, you'd probably like to check the spacecraft out before you take it out and go do an EVA with it, 75,000 kilometers off the surface of the moon for the first time. So there may be some advantages if we find an object that's a little bit later, but we'll stay with that same timeline. So they're not totally all tied together. These things are not all linked. We'll continue with these programs moving forward at the pace they can, and then tie them together into this mission when it makes sense.
If I'd add, I think that's one of the beauties and benefits of the highly efficient, extremely efficient, right, high-power solar electric propulsion. It does give you flexibility in where you want to go, how far you want to go, how long you want to go.
And the other thing that's nice about this deep retrograde orbit is the objects there can be there for an extended period of time, which is really nice. So then you could actually potentially even move the robotic spacecraft off of the object, leave the object there to go visit as an object by itself, to go look at other techniques, and actually repurpose the robotic spacecraft for another activity to go to a different region to gain more information. So if you think about this, we're really starting to toy with how we look at this in a different way. We repurpose each one of these pieces a couple times, and they feed forward into the broader reach of human exploration.
Thank you very much.
Hi, my name is AJ Kothari, president of Astrox Corporation. A question about solar electric propulsion, actually. Very interesting idea and very useful. Obviously, it has very high ISP, but low thrust. So I was wondering if you have done, and this might be a little too detailed for now, but have you done system level analysis of that type of propulsion, which includes the obviously additional weight and perhaps additional incidentals, foods, etc., that would be required, as opposed to some other types of higher thrust and low ISP venues?
Right, no, it's a good question. And so, yeah, so we have a team led by our Glenn Research Center, along with JPL, Jet Propulsion Laboratory, that have looked at the system trades for this robotic mission for some time. Then there's trades, as you mentioned, on ISP, kind of a measure of the efficiency, right, as well as the thrust level required to carry the spacecraft, the robotic capture piece, and then, of course, looking at, as Bill mentioned earlier, does it have enough delta V to move? How large of a rocket can it move? And so we have that team has a trade space, with margin. So we have a baseline concept looking at the 2,000 to 3,000 second ISP type numbers, and a rough estimate of what delta V we need, how much fuel, xenon fuel do we need, and it's a lot. It's an order of magnitude more than what we've ever done before. which is kind of an interesting aspect about the tanks and so forth, and the infrastructure that's needed, right, for that propellant. So again, the early system trades are done. I think they're even, above and beyond napkins. The napkins were started; those are put away now, right? So it actually has the analysis, and that gives us a starting point, right, to go forward with. Is it feasible? Can we do this? What are the technical challenges? What do we need to worry about? And what are some of the risks that we need to reduce? And so I think the team, like I said, led by Glenn and JPL, great start on putting that together.
All right, we have another question from social media, and we're actually going to let you panel folks off the hook for just a second, and the Deputy Administrator is going to take this one. And the question is, why is Congress trying to kill the same asteroid missions you are describing?
You gentlemen can thank me later. It was certainly a disappointment to have, as we've seen in the draft authorization bill from the House leadership, a lack of a recognition yet, I will say, of the importance and value of this mission. It really speaks to, I think, why we're here today, why we are describing for you more detail. We obviously have not completed our work, and this is the beginning of a process. And keep in mind, one of the things that the draft bill says is that we wouldn't be able to proceed until these things were explained. We are ahead of the game in explaining them. The details that this panel laid out, I think, are so compelling, from the observations importance to the technology to this goal of human space exploration on our way to Mars, and how this relates to the grand challenge that there is such universal support for, of being able to protect the planet. So just the fact that this team has gotten it this far, as I saw these charts earlier and have had the privilege of these gentlemen being able to explain to us and to start that work with our stakeholders in Congress, I think that we really, truly are going to be able to show the value of the mission. And to me, this is something that is what we do in this country, right? We debate how we spend the public's money. And this is the beginning of the debate. We are proceeding the way we have for so many missions, being able to initially outline a concept, but make it better. So we don't, in this case, just need to explain it better. We need to align it better. They talked about a concept that we're looking at that would align it better with those things that we know Congress is driving us to do, this very committee is driving us to do, and that is detect those threatening asteroid population. And if we can get a concept that aligns that better, that might be a way to proceed. We're going to tie that in with all of the ideas in this room and on the internet to make this the best mission possible. And at that point, we believe, through our work on the Hill, we will be able to have a very successful exploration plan, planetary protection plan, and ability to discover all the science, as John outlined as well. Amazing thing to have this team together, and to me it is really indicative of how NASA is going forward, not just with our asteroid strategy, but with so many of our activities. Thanks for the question.
Thank you, Lori. Well, with that, I think we're done with taking questions from the audience today. Don't fret. You can submit, again, your questions and also your ideas through the request for information that will be posted online at www.nasa.gov/asteroid initiative starting at 11:30 after this event today. We will be taking questions through that RFI as well, and plan to have a Google Plus Hangout later in this month to address some additional questions that come in through that RFI. So not your last opportunity to ask questions. Please make sure to do so through the RFI process as well. So with that, I'll say thank you to our panelists. Let's give them a round of applause. And thank you as well to all of the folks that boldly ask questions in the audience and through social media. We appreciate it. And again, remember to follow us at NASA and also be continuing to ask questions for the second question and answer we're going to have just in a little bit at #AskNASA, as well as just generally talking about this asteroid initiative conversation with the NASA Asteroid hashtag as well. So, like I reminded you right after Lori and Tom kicked us off this morning, the Asteroid Initiative is two parts. It's the asteroid mission, which we just heard from the panel on, as well as the Grand Challenge. We now have the pleasure of hearing from Jason Kessler, who is the program executive that will be leading this Grand Challenge for the agency, to tell you a little bit more about the Grand Challenge work. Jason is the program executive for this effort. Again, it's to find all asteroid threats to human populations and know what to do about them. Prior to joining OCT at NASA, he served as the Deputy Project Director for the Surveyor Project, which is a unique partnership between NASA and the USAID to bring Earth science data to the developing world for improved science-based decision-making. Jason is himself an entrepreneur, having co-founded a company who invented, produced, and distributed Holmato, which was the first organic agave ketchup company in the world in the late 2000s. Prior to honing his entrepreneurship chops, Jason began his career at NASA in the 90s, ultimately serving as NASA's Deputy Chief of Staff. Please join me in welcoming Jason to the stage.
Thank you. Thank you so much, Jen, for the introduction. My brother recently reminded me to remember to savor every moment. And I must say that this is a very easy moment to savor. I have the opportunity to follow this august panel discussing a new way of doing business, the announcement of a release of an RFI to engage the community. We've already begun the conversation and look forward to the questions that will follow and the ideas that we will get back through that RFI. If I could have the next slide, please. The Grand Challenge is something that NASA's been working through for almost a year now, and it feels really fantastic to be able to start publicly talking about it. And you see the challenge statement before us: find all asteroid threats to human populations and know what to do about them. I must let you know that there is not an imminent threat that we know about. This has not come about because something is headed our way. This is a recognition of the world that we now live in. We are more connected. We have more computer power in our handhelds. We have better educated population in the world. And this is an opportunity to take advantage of all those aspects. How can we engage a broader community in a conversation that affects every single person on this planet potentially? And so this is an effort to call to action those that might not be working or thinking about this issue to participate. And I also want to assure you that there are a lot of really smart people already working on this. As Tom Khalil mentioned, just 2 months ago, out in Flagstaff, Arizona, the IAA Planetary Defense Conference gathered more than 200 experts, world experts, focused on this very topic. So there is an A team out there working on this. Napoleon Dynamite would say they have mad skills. And what we're talking about doing is enhancing and accelerating their work. If we could go to the next slide, please. I had to have the obligatory eye chart. It's probably really hard to see from there. Basically, what I'm trying to communicate here is that there are, as I said, a lot of people working on this. Dr. Grunsfeld mentioned the leading discoveries that NASA, through the NEO program and Lindley Johnson's network, has contributed to. In addition, there are communities all over the world participating in this right now. But one of the things that we're focusing on is that piece of the pie that's not finished. And over on the right is potential contributors. These are the community that likely aren't really even thinking about this issue. And it's through the Grand Challenge, this call to action, that we want to engage in this broader conversation. If I could get the next slide, please. Here we see some notional ideas, potential opportunities for enhancing and accelerating the work that we're already doing. The first on the upper left is light curve analysis. Dr. Grunsfeld mentioned that as a characterization technique. In this global population of almost 7 billion people, there are only 50 to 100 amateur astronomers contributing to light curve analysis work today. It's mind-boggling to me to think that even as difficult as it is to do, that we can't find more people to contribute. As Dr. Grunsfeld mentioned, the number of detection is going to go up. NASA's enhancing its ability to find these, and we're going to need people to assist in the characterization, because once they're found, if we don't characterize them quickly, they're potentially gone, and we might not catch them again. So an incredible opportunity for us to think about engaging broadly in a conversation of how do we increase the real science contribution from the community to contribute to light curve analysis work. Another concept, shape model characterization. Really tough stuff. But we have, again, an enormous wealth of brain power and connectivity now that would likely be able to help us improve that as well. And then finally, space-based observation. I think everybody recognizes that to get to the next level, we really need to get off of planet Earth to continue the search. Because again, as Dr. Grunsfeld chart shows, we've done a very good job on the big ones. It's the smaller ones that do have some potential threat that we have a lot of work yet to do. There are a lot of people. You can see the enhancement in that bottom circle, a lot of potential opportunity in partnership and leveraging through a space-based observation effort. I'm going to next talk about 4 examples that NASA has utilized effectively in terms of engaging the public. And these are some ideas of how this grand challenge might work. If I could get the next slide, please. Public-private partnership. An amazing opportunity to be able to leverage the work that already exists. We have a non-reimbursable Space Act agreement with B612, a really exciting nonprofit raising private funds to send an infrared telescope into Venus-like orbit to dramatically increase the number of discoveries. This is an example of a mechanism that NASA has at its fingertips that we look to hopefully utilize in other aspects of this challenge. Next slide, please. Prizes were mentioned. NASA has a tremendous history of utilizing prizes as a way of incentivizing new thinking, engaging a new community. Here we have the level 1 winners from just a couple of weeks ago on the robot sample return. This is an opportunity to engage a community that isn't necessarily working on this, incentivizing them to bring their brain power and commitment to help us with work that we need done. Likely, an opportunity for incentivizing solutions or techniques to help us with this effort to find all asteroid threats to human populations and know what to do about them. Next slide, please. Crowdsourcing. The Zooniverse folks have shown the tremendous success that reaching out to the broader community can bring to processing huge data sets. Galaxy Zoo, an enormous Hubble data set, managed to classify galaxies with the aid of the general public much, much faster than was ever anticipated. We have a large data set already associated with asteroids. Are there ways that we can creatively bring people in to help with this problem? And next slide. Citizen science. Dr. Grunsfeld also showed a high school student detecting an asteroid in an already known data set. Lori Garver mentioned the Operation Moonwatch, which predates NASA. Here we see gentlemen from South Africa that were pulled into that effort. This is truly a global issue. This is going to require the best from everyone around the globe, And citizen science is likely a really fantastic way to engage and provide meaningful content to solving this problem. Next slide, please. And as was mentioned before, there'll be an RFI released. We're asking for ideas. How can we improve, accelerate, and enhance the work that we're already doing? This is an opportunity for every single person in the room and online watching to think about what they can do or their network, because this is about connecting across a vast population to start focusing and addressing this very, very important issue. Its international aspects cannot be understated, and in fact, Charlie Bolden is in Vienna at the UN Copious this week, talking with our partners. And for me, I think one of the most exciting opportunities that we can see here in this initiative is that it brings together this grand challenge effort where we're really reaching out through participatory engagement to engage a broader audience to assist with accelerating our planetary defense efforts, and an asteroid redirect mission, bringing together these 3 mission directorates in a way that we haven't done before, and where that overlap in terms of engaging the community. I think this is an incredible example today of what we're talking about here. And in closing, I was a fortunate child to have lived not too far from the Museum of Natural History in New York City and spent a lot of weekends there. I think one of the researchers at the museum noticed and invited me back into a lab, and it happened to be the place that I spent most of my time, and that was in the dinosaur hall. And I think, like most kids, I was utterly fascinated by these wild, magical beasts. And when I was back in that lab, I was handed a fossilized piece of dinosaur bone. And I didn't, I think, have the capacity to really connect to the meaning of that. But as I stand here before you and I think about the opportunity that we have as a population to truly take control of our own fate and figure out how we can come together to address such a problem, that we do have the ability to prove that we are smarter than the dinosaurs and take control of our own fate. And so with that, I will close and welcome any questions about how this new way of doing business might work.
Let's give him a round of applause. So again, just to remind the folks in the audience, we'll be taking questions with the microphone runners, as well as through social media. We're going to start with the social media question, but for all of y'all watching online, you can ask a question at hashtag #AskNASA to make sure that we get your questions. So with that, we'll start with social media.
All right, our first question is, how will you engage international collaborators, and do you have plans for education?
Great question, thank you. That's one of the really exciting aspects of this effort is we have so many tools at our fingertips. In terms of international collaboration, as was mentioned first by Gerst, the RFI is being released and it's open to everyone. The opportunity there is, and one of the questions that we're asking is, how can we do this better? How can we engage you? The question earlier about people and hackers that don't necessarily know about RFIs, we need help in figuring out how best to reach out. We've got some ideas, but our ideas aren't going to be the best. And so this is a new way for us to move forward, and we'd appreciate your input in that. In terms of education, I mentioned the light curve work, and our goal is to increase from the 50 to 100 amateur astronomers that are contributing to that analysis. How exciting would it be if we could engage university programs where students are already working in that field to see if we can have them work on projects to study and develop light curves, because it could be research for them to apply to their degrees and provide us valuable data as we move forward. So that's just one idea for engaging the educational community.
Harold Reitzema, B612 Foundation. I would like to emphasize just how grand the grand challenge is to find all of the potentially threatening asteroids out there. Right now, we have found about 10,000 out of approximately 500,000 to 1 million of these objects. And we find about 1,000 a year at the current rate. For instance, SpaceX at the WISE Observatory found 129 of these in a year. And so the grand part of this challenge is to increase that detection rate from 1,000 a year to something like 100,000 a year, so that we complete the survey and achieve that all level in a realistic time frame.
Thanks so much, Harold. I think part of why I get so excited about this call to action and the social movement really that we're trying to create is that that's a conversation that needs to be had. We need people to recognize what we're trying to do and get the best ideas on how to do that. So sparking that conversation is exactly what this is about. And thank you for asking, because it needs to be out there in the public domain.
Okay, and Jason, I think it'd be great too if we could address the question that was previously asked by James. So do you remember, would you like me to get him to re-ask it?
If you could re-ask it, please.
I will run right back over there.
You just mentioned it, but my question was about citizen scientists that aren't directly involved with NASA. How is it that we get information about what to do next? Like, I've been in contact with the team that I worked with during the Space Apps Challenge hackathon, and everybody is unbelievably excited about this. It's a bunch of people who, much like you, spent their youths in planetariums and dinosaur halls, and glaring at beautiful images being returned from the Hubble and all of NASA's different space missions. And now everybody's chomping at the bit to do something that they didn't realize they were capable of doing. And it's been this kind of amazing, transformative experience for a lot of the people involved. And we really want to do something. We really want to put our small mark on this project. And even if I were to take a look at the RFI, I'm not sure I'd know what I was looking at. So, so any help with that would be incredible. And I also want to really encourage NASA to continue these community outreach programs. Like, you have no idea how this changes people's lives, especially young people that came to this hackathon who have never been told that they're capable of doing this. A lot of there were young kids from a few inner city schools around Manhattan that participated, and these kids blew my mind. I mean, we had people building software that could do things that nobody would assume these young kids could do, and so that was both a question, I think, and a statement, but in there somewhere is information.
Well, appreciate the statement. It's great validation for something I think the agency strongly believes in. In terms of the question, I didn't go into great detail about what our summer plans are. The RFI will be released. We expect to hopefully get some good ideas and guidance back on effective ways to move forward. We also anticipate initiating some digital brainstorming sessions. We found those to be quite effective in the past. And all of this summer planning will lead up to a fall workshop where we want to build some tracks based on the input that we're getting to develop a pathway, an implementation plan on how to approach this issue by recognizing where we are right now, where we're trying to get to, and what are the steps we need to take in between to make that possible. And so the RFI is our first step. I would guide you, I think, well, it's off the screen now, but nasa.gov/asteroid initiative will be the easiest way to find material. And there'll be information on the digital brainstorms. There'll be information on the fall workshop. And so that's probably the best way for us at this point to stay connected. Certainly we have, through the connection already with the International Space Apps, the list of participants, and hopefully through that list we can engage you directly, and then the networks that you have that aren't part of that would be fantastic as well. Does that get your... Yeah. Great.
Hi, Rick Tomlinson, Deep Space Industries. Congratulations on this. I mean, you're getting right in there, and this is exactly what needs to happen. And while the missions that were being talked about here, while they take place in a vacuum, obviously, what you're doing is not going to take place in a vacuum. And we have people down the street, as Lori addressed, who are going to have some other ideas. How do you, there's two things that are going to go on, possibly. People are going to attack the budget. They're going to try and chop it down. They're going to say you have to do these other things first before you do this, et cetera, et cetera. And what that's going to mean in the ears of a lot of people in the agency in particular is this is going to chew away at my slice of the pie. And then you're going to bring in all these great unwashed civilians and kids and people who are also going to be doing things that are going to maybe challenge some of the funding sources of people who believe they have to have them coming into their center or into their staffs or into their projects. So you've got a great outreach campaign that you're starting right now. Will there be an equal and hopefully stronger in-reach campaign throughout NASA and all of the centers to begin to educate the people at the agency that this is something that's actually going to help them in the long run, and that there's a new game in town, and it's called working together, all of us working together in a common cause. Because the excitement that'll be generated by the kids that this gentleman was speaking about will reach into their parents, will reach into their communities, and trickle up to those people down the street. And in the end, everybody's going to get more support. So are you guys going to be working inside of the agency?
Absolutely intend to work with inside the agency. The recognition that we have such an incredibly smart, bright, committed workforce that it would be foolish of us not to do so. And one of the first steps for us is exactly that, to reach out to all the centers. Centers have, I've worked at 2 centers, they all have different cultures. We're going to need to figure out how to engage with each center appropriately, but from what we've already discussed, there is a tremendous amount of interest in this, and really look forward to the great partnership internally that we are going to have as we move forward with our planning.
Rick, if I could comment to your question. We've already started that process. I will tell you that, to Jason's comment, our teams are pretty excited about this, and they're actually pinging us about how do we get involved. Some of them were even surprised we put NASA centers on the RFI, that the NASA centers could even submit in there, because we have had a small team working this, and we want to take advantage of all those ideas as well. So our goal here is a change in, I mean, just today to me is a change in how we're doing this. And so we're rolling this out in a way to try to explain to our team that there are other ideas out there. Let's make sure we know what they are before we go in. But we even have that internal. That's an internal cultural issue we're dealing with as well in the agency, and our teams are excited. We've had, during the budget rollout briefings where me and Lori and Charlie have gone out, I mean, it's totally different than what it's been in a long time. People are coming up to us telling us what they want to do, how they want to do it, and this is going to be the challenge for us. The 4 of us are going to have to deal with all these ideas and ultimately decide on something. And that's going to be a challenge as we move forward. But as long as we always have that future piece in our head is, look, we're all trying to just keep exploring. That's what we're trying to do. And as long as what we're doing and all the pieces that we're doing, whether we're worried about protecting the planet or planetary defense, or whether we're trying to ultimately get people further than we've ever taken before, that's got to be our big litmus test. It's the gate everything has to pass through. And most of our teams are, I mean, I would say there's nothing, as I like to say, there's nothing malicious. Everybody just wants to help. And so we're trying to get all those ideas in before we get completely baked. But it is a cultural thing. We recognize that, and we're already starting to work that internally.
I think Lori mentioned that this is a $20 million effort in the 14 budget. Is that in addition to the 105 for the asteroid capture work, or on top of that? And then could you give us a little bit on just exactly how you hope to spend that initial $20 million, and if you plan to have out-year funding as well?
So the 105 is for the overall initiative. And the 20 million that Lori described was focused on doubling the NEO budget. So that is for enhancing our observation efforts. That's where there's the most obvious overlap between the redirect mission and the Grand Challenge. In addition, out of that 105, there is $7 million. We don't know exactly how that will split between mission and Grand Challenge overlap and Grand Challenge specific. That's for space tech and early stage grants and Centennial Challenge. And outside of the 105 is $1 million for Office of the Chief Technologist to have the ability to coordinate and work on some mitigation road mapping. And so that's how that money breaks.
So the 20 is in the 105?
Yes, it is. You're welcome.
Hey, Jason. Chris Lewicki again, Planetary Resources. We're in the middle of a first-of-its-kind kind of effort where 10,389 individuals have pledged their support to enable a public part of our component of private exploration. And as a small company, we've got a challenge in front of us to engage with everyone who's really excited about what we're doing. How does NASA plan on coordinating and cooperating with thousands or tens of thousands or hundreds of thousands of individuals to help each of these gentlemen down in the front of the room with their directorates in achieving NASA's goals?
Great question. I don't have all the answers right now. This is new for us. The intention is to start getting the ideas within the next month. I think one of the great things about this RFI is that we can hopefully begin a dialogue on how to do this better. You've got some experience. Congratulations on what you have started. And so this is going to be a learning process for us. And so I don't have it all nailed down yet. It is an invitation to begin a dialogue and a conversation to figure out how to do it effectively. And our goal is to keep our eyes wide open and engaged in the conversation as we move forward. So in a year, I'll probably have a better answer for you, but at this point, I don't want to bound it.
All right, let's go ahead and give a round of applause not only to Jason, but all of our speakers today. We want to thank you all for joining us both in person today for this event, as well as online, following on the Ustream channel for the Asteroid Initiative Partner and Industry Day. This has been recorded and will be able to be accessed on YouTube if you'd like to, again, share it with your friends or rewatch it. We look forward to your ideas through the RFI. Quick reminder that that deadline is going to be July 18th, so make sure to pull it down from the website at www.nasa.gov/asteroid initiative today to start working on your questions for that, which we will address at a Google Plus Hangout later this month, as well as your inputs that are due by July 18th. You can also find the presentations from today's event online at the same website, www.nasa.gov/asteroid initiative. I know some of them are eye charts, but you'll be able to see them in their full online thereafter. Please remember to follow NASA on all of our social channels and keep the dialogue going on this topic with the hashtag NASA Asteroid. And thank you very much for joining us today. This concludes our program.